We have ignition. We have a liftoff.
Most distant human-made object, NASA's Voyager 1 spacecraft, is in interstellar space, the space between the stars.
For over 4 decades, Voyager 1 has been on a quest for interstellar discovery, steadily moving away from Earth and venturing into the unknown parts of the universe. Recently, the spectacular probe sent a strange warning message that has shocked scientists as it points to the possibility of a new elemental force in the cosmos. Michio Kaku, one of the world's leading physicists, has finally shed light on this mysterious new force and why it specifically appeared now.
If we make contact with them, I think in this century, we'll probably pick up signals from an extraterrestrial civilization.
Join us as we explore the implication of this new force and how it's connected to the formula that describes all of creation. In 1977, NASA took a bold step that forever changed our understanding and interaction with outer space. It was the year when Voyager 1, an extraordinary spacecraft, was launched. The primary purpose of Voyager 1 was to actively explore and gather scientific data about our solar system, particularly focusing on the outer planets and their moons, and ultimately venture into interstellar space. Throughout its mission, Voyager 1 achieved remarkable milestones. It successfully conducted flybys of Saturn, Venus, Uranus, and Jupiter, surpassing all expectations. Eventually, it went beyond the confines of our solar system. Now, after 4 decades, an unexpected incident has occurred. Recent readings from Voyager 1 indicate the presence of a completely new elemental force. This discovery has sent shockwaves through the scientific community and sparked curiosity amongst the public. Before we dive into the insights of renowned physicist Michio Kaku regarding this mysterious force and the formula that allegedly accounts for all the universe's creations, it is essential to understand the profound significance of this remarkable space probe. Voyager 1. Voyager 1 holds the record for being the farthest human-made object to have ever left Earth. It was launched by NASA on September 5, 1977, as part of the ambitious Voyager program aimed at exploring the outer planets of our solar system. The spacecraft, which included Voyager 1 and its twin, Voyager 2, was equipped with advanced scientific instruments and cameras to gather valuable data and capture images from distant space. One of the most remarkable aspects of Voyager 1 is its golden record, which can be likened to a message in a bottle sent out into the universe. This special record is meticulously engraved on a disc made of copper plated with gold. It contains a remarkable assortment of sounds and images that offer a glimpse into life on Earth. From the majestic sounds of thunder to the timeless melodies of Mozart. From warm greetings expressed in 55 different languages to a map showing our position in the vastness of the galaxy, this record serves as a time capsule representing our species' culture and knowledge. Moreover, it acts as an open invitation to any potential extraterrestrial civilizations that might come across it, inviting them to explore and engage with the essence of our existence. Voyager 1's journey through our solar system has been nothing short of astonishing. It conducted flybys of Jupiter and Saturn, sending back invaluable data about their atmospheres, moons, and magnetic fields. It was Voyager 1 that captured the mesmerizing images of Jupiter's great red spot and Saturn's majestic rings, images that continue to captivate and inspire to this day. But Voyager 1's mission didn't stop at the outer planets. It carried on, hurtling through the void of interstellar space, where no spacecraft had visited before. This remarkable achievement occurred on August 25, 2012, when Voyager 1 officially crossed the boundary known as the heliopause, leaving the influence of our sun's solar wind behind. It became the first human-made object to enter interstellar space, a monumental milestone that marked its transition from an explorer of our solar neighborhood to a messenger from the cosmos. The spacecraft's resilience is nothing short of remarkable. Despite its age, Voyager 1 continues to communicate with Earth from its incredible distance of over 14 billion miles, 23 billion kilometers. Its signals, traveling at the speed of light, take more than 21 hours to reach us. The fact that we can still hear from Voyager 1 after all these years is a testament to the engineers and scientists who meticulously designed and maintained this intrepid explorer. The instruments aboard Voyager 1 continue to make discoveries even in its interstellar journey. For instance, it detected the first ever sounds of interstellar space. A faint but strange hum sound caused by the vibrations of charged particles in the cosmic emptiness. These findings provide valuable insights into the nature of the interstellar medium and the environment beyond our solar system. One of the most fascinating aspects of Voyager 1's mission is its longevity. Originally designed for a mission lasting just 5 years, this spacecraft has defied all expectations, continuing to send back data and images long after its creators had anticipated. Voyager 1 was equipped with something called a radioisotope thermoelectric generator, or RTG for short. This RTG made use of the decay of a radioactive isotope called plutonium-238 to generate electricity. Plutonium-238 isn't something you find just lying around. It's produced in special nuclear reactors. The process involves irradiating another isotope called neptunium-237, which then undergoes radioactive decay to transform into the precious plutonium-238. It takes several steps, including irradiation, separation, and purification, to obtain the desired isotope that powers Voyager 1. Imagine this: a stack of thermocouples arranged cleverly within the RTG. These thermocouples are made of different materials, and when exposed to the heat from the decaying plutonium-238, they create a temperature gradient. It's like a thermal dance party happening inside the spacecraft. This temperature gradient is what generates an electric current using a phenomenon called the Seebeck effect. That electric current is the lifeblood that powers Voyager 1's instruments and systems. When Voyager 1 set off on its grand journey, its RTG was a powerhouse, producing a whopping 470 watts of electrical power. But as time went on, as it ventured further and further into the unknown, the power output gradually declined. The half-life of plutonium-238 is about 87.7 years. That means its power output decreases by half every 87.7 years. So, the current power output of Voyager 1's RTG is estimated to be around 250 watts. Still impressive, considering the decades of extreme conditions it has endured. Voyager 1 recently had an unusual encounter that made the spectacular spacecraft send bizarre messages back to Earth. These strange signals have stirred the curiosity of scientists, leaving them with a perplexing puzzle to solve. Some experts hypothesize that a malfunction may be at play, prompting a quest to decipher the issue and seek potential solutions. In this pursuit, scientists are delving into unconventional theories that have garnered attention within the scientific community, one of which is the captivating concept known as the God equation. Renowned theoretical physicist and City University of New York professor Michio Kaku has long been fascinated by the God equation throughout his illustrious career. For 3 decades, Albert Einstein dedicated himself tirelessly to the pursuit of an equation with a profound objective: to unify the 4 fundamental forces of nature. These forces encompass gravity, electromagnetic force, and the 2 nuclear forces. In Kaku's vision, the grand quest is to formulate a theory of everything, an all-encompassing equation that embraces the fundamental principles of physics. Drawing a parallel to Leonard Euler's equation in mathematics, which elegantly encapsulates essential constants, Kaku named this theoretical masterpiece the God equation of mathematics. Does the Voyager 1 have a problem, and can Michio Kaku's God equation solve it? Michio Kaku, the Japanese-American researcher, holds a similar influential position in the United States as Stephen Hawking did in Europe. Born in California, Kaku developed a passion for physics and the cosmos from a young age. He pursued theoretical physics, proposed theses, and authored numerous best-selling books aimed at helping ordinary people grasp a deeper understanding of the universe and its creation from a physics perspective. Kaku is widely regarded as a visionary and has emerged as a superstar among physicists. In a recent interview, Kaku addressed the intriguing measurement data from the Voyager 1 probe, which has raised questions about the possibility of encountering an unknown force. He acknowledged the potential for contact with such a force, but the question remains whether it could provide another key to unifying the grand field theories. However, certain branches of science still present arguments against this notion. The unification of field theories would be represented by what Kaku and his English-speaking colleagues refer to as the God equation, a single formula capable of describing all phenomena and forces in the cosmos. The implications of such a formula extend far beyond our current understanding. To fully appreciate the significance of the Voyager 1 discovery and the gap between theoretical physics and quantum mechanics, it is essential to comprehend the problem at hand. The field of theoretical physics deals with large-scale phenomena, encompassing planets, galaxies, the forces at work, and the rules governing their dynamics and interdependencies. Well-established works in this realm include Einstein's theories of relativity. On the other hand, quantum mechanics emerged much later and allows us to delve into the subatomic realm. Technological advancements have enabled researchers to study elementary particles like quanta, quarks, and neutrinos, albeit indirectly. The effects and behaviors of these particles are observed and studied within facilities such as the Particle Accelerator in Geneva. This progress would have been unimaginable centuries ago when people relied solely on simple telescopes to observe the skies. The foundations of classical physics are largely based on visible, measurable, and experimentally provable phenomena. For instance, while gravity itself is invisible, its effects are observable and experienced by all, as demonstrated by the falling of an apple or the firmness of our feet on the ground. Isaac Newton, the English natural scientist, was the first to define physical forces as movements and dynamics. However, it was Albert Einstein who ventured into the realm of subatomic particles, such as photons or quanta, at the beginning of the 20th century. In fact, Einstein received his Nobel Prize for this contribution, rather than for his theory of relativity, as commonly assumed. Throughout his life, Einstein recognized the groundbreaking nature of his discoveries, but he also realized that they were insufficient to describe the entire cosmos. He tirelessly looked for a unified field theory, a formula that could encompass all phenomena and forces within a single scientific statement. However, Einstein grappled with the challenge, rejecting quantum physics and famously asserting, "God does not play dice," referring to the probabilistic nature that seemed to govern the subatomic realm, which contradicted his worldview as a physicist. Born in 1947, Michio Kaku encountered quantum theories during his studies and recognized that the 2 branches of physics were not mutually exclusive. Kaku recognizes the practical applications of physics, as each force discovered in the past has had a profound impact on human history. Newton's work on mechanics and gravity laid the foundation for the Industrial Revolution, while Maxwell and Faraday's unification of electricity and magnetism led to the Electric Revolution. Einstein's famous equation, E=mc², paved the way for understanding the nuclear force. Each breakthrough in physics has reshaped the course of humanity. However, a significant challenge arises when attempting to unify the two pillars of modern physics, relativity and quantum theory. Einstein's general relativity, which describes the behavior of gravity in terms of smooth space-time curves, clashes with the quantum theory, which deals with discrete particles and their interactions. This disparity between the two theories has made the quest for a unified theory all the more difficult. Kaku acknowledges that numerous brilliant minds throughout history have proposed theories of everything, but each attempt has fallen short, often plagued by divergences and inconsistencies. However, there is one theory that has withstood these challenges: string theory, which Kaku himself specializes in. String theory proposes that at the fundamental level, particles are not point-like entities, but rather tiny vibrating strings, akin to the strings of a guitar. The different vibrations of these strings give rise to the various subatomic particles observed in nature. The beauty of string theory lies in its symmetries. It allows for the interconversion of particles, transforming electrons into neutrinos or neutrinos into quarks, while the theory remains consistent. Kaku believes that string theory is the only mathematically consistent theory among the contenders. Other theories tend to exhibit mathematical inconsistencies that undermine their validity. String theory, on the other hand, maintains internal consistency, providing confidence in its potential as the elusive theory of everything. However, string theory faces its fair share of objections. One of the major criticisms is the lack of experimental tests, making it difficult to confirm its validity. Nevertheless, Kaku remains optimistic that advancements in technology and scientific understanding will bring us closer to testing the theory. The implications of a theory of everything are mind-boggling. It opens up the possibility of time travel, the existence of wormholes that connect distant parts of the universe, knowledge about what came before the Big Bang, and the existence of parallel universes within a multiverse. How can the God equation help us solve Voyager 1's possible malfunction? Before we get into the big question, it's important to understand that this isn't the first time Voyager 1 is having a malfunction. That's right. In 1980, Voyager 1 faced a major challenge related to its gyroscope, a crucial component responsible for maintaining the spacecraft's stability and orientation. The gyroscope helps determine the spacecraft's position relative to its intended path and makes precise adjustments to keep it on track. However, anomalies in the gyroscope's functionality were detected, causing concerns among the mission operators and engineers. These anomalies affected the accuracy of Voyager 1's attitude control system, potentially leading to deviations from its planned trajectory. To address this issue and ensure the spacecraft stayed on course, a dedicated team of engineers and scientists worked diligently to identify the root cause of the problem. They conducted thorough analyses, studied telemetry data, and performed simulations to uncover the source of the anomalies. After extensive investigations, it was determined that the gyroscope anomalies were likely caused by aging components and the harsh environment of space. To mitigate the impact of these anomalies, the team devised innovative solutions. They implemented software updates to compensate for the gyroscope's reduced accuracy and recalibrated the attitude control system to maintain the desired trajectory. These efforts successfully stabilized Voyager 1, enabling it to continue its mission and provide valuable insights into the outer regions of the solar system. Now, you may be wondering how a technologically outdated probe from the 1970s is related to the solution of the elusive God equation. Well, the connection is both simple and complex, as scientists find themselves divided once again due to the current data received from the probe. I'll present you with the facts. In 2012, Voyager 1 achieved a historic milestone by becoming the first human-made object to cross the boundary of our solar system. Our sun emits a stable stream of particles, creating an enormous bubble known as the heliosphere that envelops the star and all the planets. Beyond this lies the interstellar medium, the space between stars, which spans vast distances in the cosmos. The main difference between these two regions lies in the forces at play and, particularly, the particle density. Within the heliosphere, the particle density is approximately 100 particles per cubic centimeter. However, once Voyager 1 ventured into interstellar space, the particle density dropped significantly to just 1 particle per cubic centimeter. This stark difference led researchers to assume that sound transmission in the cosmos is either impossible or severely weakened. The sound relies on particle oscillations, and where there are no particles, oscillation transmission is theoretically absent. Until now, our knowledge of interstellar space relied on mathematical and physical assumptions, as well as observations of faint oscillations, such as gravitational waves. However, Voyager 1 surprised us with its entry into the interstellar medium, revealing a denser and more stable boundary than originally predicted. Researchers measured strong solar winds during Voyager 2's boundary crossing, expecting this to cause an expansion of the heliosphere. Yet, Voyager 2 transmitted the same data as Voyager 1, challenging previous assumptions and leading to revised understandings of the interactions between the interstellar medium and the heliosphere. Over the years, Voyager 1 has continued its journey, traveling at a speed of nearly 37,000 miles per hour. Astonishingly, the probe still reliably sends data back to Earth, despite taking several hours to reach us. These transmissions are captured by dedicated antennas that have been specifically erected for this purpose. But how is this possible? The density of particles and the ability to transmit radio waves in interstellar space continue to decrease. Perhaps another intriguing discovery made by the Voyager probe will shed light on this mystery. In 2022, Voyager 1 reported data anomalies that initially led researchers to suspect a technical malfunction. However, after a short period, the data stabilized, leaving some scientists to believe that the probe experienced age-related failures, while others considered the possibility of an unknown force at play. This has given rise to the Voyager paradox. Due to the staggering distances involved, Voyager 1's signals travel at the speed of light, requiring over 22 hours to reach the Earth. Consequently, any instructions or commands we send to Voyager 1 experience a considerable time delay before reaching the spacecraft itself. This peculiar situation gives rise to a fascinating conundrum. Voyager 1 operates based on instructions that were dispatched from Earth in the past. In other words, the spacecraft finds itself out of sync with the present state of affairs on Earth. If we were to observe Voyager 1 in real time from its current location, we would witness it executing commands that were transmitted many hours ago, rendering them outdated to Earth's present time. The Voyager paradox poses captivating questions that delve into the realms of communication, time, and our perception of events in the vast reaches of space. It challenges our intuitive understanding and serves as a poignant reminder of the immense timescales and mind-boggling distances involved in interstellar exploration. Renowned physicist Michio Kaku advises caution in interpreting the recent discoveries, emphasizing the need for thorough scientific studies to confirm any new forces encountered by Voyager 1. Could this mysterious force be the missing piece of the cosmic puzzle? Could it provide us with insights into cosmology and creation? These questions remain open, and further exploration is required to obtain conclusive answers. If we were to understand the God equation, humanity would not only gain a deeper understanding of creation, but also wield the power to actively shape it. The possibilities would be both simple and extraordinary. Thanks for watching. Check out the video you see on your screen.